So what we're looking at is your inverse and exponential functions. First things first is to find an inverse function. All we need to do is we need to change our x and y, and then we need to solve for y. So to do that, add 4, obviously, equals y squared. Take the square root, so I have the square root of x plus 4 is equal to y. Now I want to use this proper notation, f inverse of x equals the square root of x plus 4. Over here, same thing. X equals 1 over y. I have that y in the denominator. I multiply both sides by y. So I have xy equals 1. Let's divide both sides by x. I get y equals 1 over x. That is my g inverse of x. So 1 over x is its own inverse. This one, x equals 5y minus 1. That means I will add 1, and then I will divide by 5 to get my y. And that is what my h inverse of x equals. And my last one, I have the cubed root here. It's going to have x equals the cubed root of y minus 2, cube both sides. That cancels each other out, and then I need to add 2. X cubed plus 2 is equal to y, so that is my k inverse of x. Alright, so on the next step, now we need to find the derivative of an inverse function. So this has many steps. First, take this number you have right here. That's what you want to set f of x equal to. Negative 12 equals 4x cubed minus 8. Solve for x. Add 8 to both sides. Now need to then divide by 4 here. And now give me negative 1 equals x cubed. Taking the cubed root means negative 1 equals x. What I also need to do, though, is I need to attempt to find the derivative of my original function. The derivative of that function is 12x squared. What I want to do from there, though, is I want to find what is f prime of that number I just found for x, of negative 1. Well, if I plug in negative 1, that's 12 times negative 1 squared, which is just positive 12. Now, the key here is that f inverse prime of negative 12 will be equal to 1 over f prime of this number I just found, of negative 1. So that is just 1 over 12. That is my answer for that. For the next one, remember, I can rewrite this function as x minus 2 all to the 1/2 power. That means if I did the derivative first, it'll be 1/2 x minus 2 to the negative 1/2 power. I can rewrite that as 1 over 2 square roots of x minus 2. I need to see what my point is going to be, so I set 3 equal to that function. I'll square both sides to get me 9 equals x minus 2, which means 11 equals x. I now want to find what f prime of 11 is, so I'm going to plug it straight into this formula here. 1 over 2 times 11 minus 2 in the square root. So that is 1 over 2 times 3, because that's 9, the square root of that is 3. So 1 over 6 is my derivative there. So this g inverse prime of 3 is the same as the reciprocal from g prime of 11, which we said was 1/6. So we got 1 over 1/6, which is just equal to 6. So that's my final answer for that one. Okay, next one. First, let's find the h prime of x. This is a quotient rule here. So I'm going to say my quotient rule of low d high. So x minus 1, d high is just 1, minus high d low. Derivative of the bottom is just 1 again, over low squared, x minus 1 quantity squared. So my x's will cancel out. Negative 1 minus another 1 gives me a negative 2 on the top, x minus 1 quantity squared on the bottom. What point am I going to be using this time? I need to find, this should be h inverse, obviously. I want to set 2 equal to my original function, x plus 1 over x minus 1. Multiply both sides by the denominator and distribute through. So 2x minus 2 equals x plus 1. Now I'm just solving for x. Subtract an x over to get an x here. I'll add 2 to both sides, so x equals 3. So this means that I need to also know what h prime of 3 is. I'm just going to plug that in. Negative 2 over 3 minus 1, the quantity squared. That's negative 2 over 4, which is the same as negative 1/2. So my final answer should be h inverse prime of 2, the same as 1 over h prime of 3. So that's 1 over negative 1/2, which is negative 2. And one final one to do here. Start by doing by k prime. K prime here ends up being 3x squared minus 2. I want to set 2 to equal x cubed plus 2x minus 1. There really is no special way to do this. Normally, if someone would be able to factor out, you can kind of guess and check if you need to, but x equals 1 ends up being the x value that we want. So that means I want to check what's k prime of 1. K prime of 1 is 3 times 1 minus 2. So k prime of 1 should just be 1. Alright, I forgot this was plus here, so I should have made this 3x squared plus 2, which means when I plugged in 1, I should get 5 as my derivative. So that means when I do my k inverse prime of 2, same as 1 over k prime of 1, so 1 over 5 should be my official answer here for number 8. Alright, let's move on to your favorite problems in the world. Actually, they should be your favorite because they're about as straightforward as they come. If I want f inverse prime of 3, when does my function equal 3? That's right here. So that means I want to take 1 over f prime of whatever this number is, f prime of 2. And f prime of 2 is just 4. So my answer is 1 over 4. For this one, same sort of idea. I need to say, when does my function equal 4? It equals 4 at an x value of 1. So I want 1 over f prime now of 1. And f prime of 1 is negative 2. So my answer is 1 over negative 2, or negative 1/2. For this one down here with the g's, same idea. When does my function equal 0? Equals 0 when my x is 5. So 1 over g prime of 5, which g prime of 5 is just 10. Tells you right there. And the last one, when does my function equal 3? Equals 3 when g is 6. So 1 over g prime of 6. G prime of 6 is 4, so my answer is 1 over 4 for that one as well. Okay, make sure you pay attention. Some people could go and say, well, when does the function equal 3? And look over here, because that equals 3. This row right here is not function values, those are derivative values. Make sure we're paying attention to just g's, not the g primes in that second row. Very important, make sure you're looking at the right spots. Alright, on to actually evaluating derivatives and integrals for differentials and logarithms here. First one we have is of an e function. The e is we just rewrite it, and then we multiply by the derivative of the inside. So multiply it by 4. 4 times e to the 4x minus 2. The natural logs, we have x squared plus 4x. We want to write that over a fraction. And then again, multiply by derivative of the inside, which would be 2x plus 4. And then I'll just rewrite that as one big fraction. 2x plus 4 on top, x squared plus 4x on the bottom. In our next one here, we're doing, it looks like an e to the x again, so it's going to be similar to that. We're going to rewrite it, 4 to the 3x, multiply by derivative of the inside, but now it's no longer an e. We need to have one more constant that we multiply by. We always multiply by the ln of, not 3, ln of 4, ln of the base. And if I rewrite this, it would be 3 times ln of 4, all times that 4 to the 3x. That would be the standard notation for it. If you left it like this, that would be alright. Okay? Same thing here. We're going to look now with logarithm. This should look like an ln function. So what we're going to do, first of all, is let's rewrite the function to begin with. We want to rewrite this as natural log of the big stuff. So natural log of 2x cubed minus 6x squared over natural log of the little guy, the little number 8. ln of 8 is just a number. I can actually pull that out in front and then just take the derivative of the thing on top. The derivative of that is ln, so 1 over the 2x cubed minus 6x squared, times derivative of the inside, which is 6x squared minus 12x. I'll just combine that into one big fraction. The 6x squared minus 12x goes on top. My bottom will be ln of 8 times the quantity of 2x cubed minus 6x squared. Alright, and this last one down here. This first one we have, number 17, we have two things multiplied, we're doing product rule. So, first times derivative of the second. It's an exponential, so I rewrite it. Multiply by derivative of the inside, derivative of the top is just 1. So multiply by 1 if I wanted to. Times, I also need natural log of the base, natural log of 6. So that's first times derivative of the second, plus the second times the derivative of the first, which is 2x, just basic power. From there, simplifying it, if you left it as ln of 6 times x squared 6 to the x plus 2x 6 to the x, that would be cool. If we looked at a multiple choice question on the AP exam, they'd be pulling out an x and a 6 to the x, and you'd be left with ln of 6 times x for the first one and 1 for the second. That might be how you would see it on a AP test, but that starting equation is the one I'm looking for. And this last one, log of x plus 2. Again, in this one, we don't have a number. However, we can always assume that it's base 10 because we're in the base 10 system. I'll rewrite this as natural log of the big guy over the natural log of the little guy. So that means when I take the derivative, so I'm not taking a derivative here. I should technically have said that here. I haven't taken a derivative yet, so keep that b dx. So that means here that I would have the 1 over ln of 10 stays in front. I'm going to do this derivative, 1 over x plus 2, times derivative of the inside. Well, derivative of the inside is just 1. So I'll rewrite it as ln of 10 times x plus 2, all that in the denominator of that fraction. Alright, so on to the last set, the integrals that we're going to do. In this first one, and pretty much all of them, you should be looking for, can I do a u and can I do a du? In this first one, I have, for my u, I'm going to do 3x squared. That way when I do my derivative of 6x dx, that way my x's will cancel each other out. So, what this will look like is, I'm going to rewrite this as now the integral. I didn't do x yet. It's now e to the u power. My dx would now be, dx would equal du over 6x. That's why I write du over 6x. What cancels each other out? The x's go away. I can pull out the 1/6 because the 6 is in the denominator. It comes out to the front. Now I have the integral of e to the u du. This is always where I evaluate the integral. The integral of e to the u is just e to the u plus c. My last step is just to plug back in for u, so 1/6 e to the 3x squared plus c as my final answer. For the second one, I'm going to make my exponent here to be my u, so u is equal to 5x minus 9. That means du will equal 5 dx. So as I go and try to set this one up, this is now the integral of 3 to the u. My dx now is du over 5. There's nothing to cancel out, but I can pull out a 1/5, 5 in the denominator, integral of 3 to the u du. Now I evaluate the integral. Keep the 1/5 in front. 3 to the u, its integral is itself. I need to divide by the natural log of the base, natural log of 3 plus c. My last step again is always just to, plug in back for u. So we're going to have 3 to the 5x minus 9 over ln of 3 plus c. You could combine it. One last step would be 3 to the 5x minus 9. Combine the 5 ln of 3 in the denominator with your plus c at the end. Alright, the next one, number 21. If I take u as my top, then my derivative, when I do it, will not be able to cancel out this entire bottom. So I need to make my bottom be my u, 4 plus 7 to the 3x plus 1, and make my du be then, what would this derivative be? It's an exponential, so I rewrite the equation. I multiply by derivative of the inside, and because my base is not e, I need to multiply by ln of the base. ln ln of, I did it again, not ln of 3, ln of 7. So when I rewrite this equation, I didn't do anything to the top, so I'm going to keep that as it was. My bottom is now u. dx would have been now du divided by a lot of stuff. 7 to the 3x plus 1 times 3 times the natural log of 7. Let's see what cancels each other out. The 7 to the 3x plus 1 should cancel out, and I should be able to pull out in front this 3 ln of 7. I'm left with the integral of 1 over u du. What I need to do from here, I now evaluate the integral. The integral of 1 over u is the natural log. So keep my constant in front, evaluating the integral natural log of u plus c. Now let's rewrite it, put it back in terms of x. So now the natural log of 4 plus 7 to the 3x plus 1 power, remember the absolute value, plus c. And actually in this case, this exponential, anything in an exponent will never be negative. So really you could make these as parentheses instead of absolute values. That would be alright. I don't expect you to fully notice that. I'm not too worried about that. Alright, our last one. What we want to look at for this is I can first split this into two different integrals. Integral of x dx plus the integral of 12 to the negative x dx. What I'm going to look at for this one is that my u is going to be, I can do this one immediately, so we'll hang on to that. But for this, I can make my u be negative x, make du be negative dx. Because I can't take the integral with a negative exponent. We don't know how to do that yet. So, what I'm going to say now, I'm going to keep the first one the same way. The second integral is now going to be, it'll be 12 to the u, and now du will be, dx is now a negative du. So I'll put the negative out in front. So now I can evaluate these integrals. I have, this will become 1/2 x squared from the first integral. The second one will be 12 to the u divided by ln of 12 plus c. And my last step always, put it back in terms of x. This already was, obviously. Minus 12 to the negative x over the ln of 12, and then plus c as my final answer. So, there you have it. All of your derivatives, all of your integrals, everything that you need to do for this test, and hopefully you'll be in good shape to get it up.